Welcome, everyone. Thanks for coming out on a very wet, chilly spring night. Does it feel like spring? Not quite yet. Interesting year. I guess it's good for fire, as they say. It's a great opportunity to be here. I came here 20 years ago, right after I became a new professor at U of O, and gave a talk just down the hall. Scott just showed me where that happened. So it's really fun to come back after so many years and talk to this group. It's an honor. Scott reminded me of something really funny that happened when I got hired at U of O. I was working in the Coast Range and a geologist, and none of the people in my department were interested or knew much about geomorphology. And they said, "Why would you do geology? There's all these trees and of all the rocks." And for me, that was heaven, is all the things that were happening in that forest. So that's what I'm going to tell you a little bit about today. But before we got there, my personal journey starts with an airplane window. I come from the topographically challenged state of Minnesota. And so seeing landscapes such as we have here in Oregon and all over the Western US was something novel and interesting for me. And I was the kid, and now I'm still the guy that pushes people out of the way to get the airplane seat in the window. And I spend most flights with my forehead pressed against that window. So these are one of hundreds, if not thousands, of photos in my collection and the things that get me excited. So just a quick little personal journey. Today, I'm going to tell you about how we can use lasers to look behind all those trees, Cascadia's green veil. And I want to contrast the perspective of North America by a French cartographer. This was taken from a volume by Brian Atwater in 1720, so 300 years ago. The French cartography world envisioned North America like this. And you can see there's something pretty big missing right there. And for Zoom people, our whole world is sort of a big question mark. There's a dashed line right there, meaning geologists don't really know what's going on back there. And contrast that today with our ability to depict landscapes in excruciatingly detail with laser pulses from above. And that's shown here with this tree, where all of these little dots are the canopy of this tree depicted by a Lidar data set. And our ability to understand the landscape is so advanced because of this technology. So what does it mean to be from this part of the world? I should ask you that more than tell you. When people ask me what it's like to be in this part of the world and do geology, for me, it's defined by two things. The first one is the subduction zone that we all know about, we live on top of, you've been hearing a lot about for quite a while. We have volcanoes, we have earthquakes, we have mountains being built because of this subduction zone, and trees. For me, I can't decouple my understanding of our landscapes in Western Oregon without the role of these big trees as entities that, you know, hide the landscape, but also shape the landscape as well. So there's all kinds of different roles they play. So before European scientists came into this part of the world, there was an amazing amount of information conveyed generation after generation by indigenous peoples. The Native American oral history of geologic processes is profound. And one of my favorite papers to give people, if they are interested in this, is by a seismologist that collaborated with an anthropologist. They interviewed dozens and dozens of elders all the way from British Columbia down to Northern California. And maybe you've heard about this. It's a beautiful, short, very readable paper that uses those interviews, uses the information that they've gathered, and they were able to independently bracket the last subduction zone earthquake to not too far off from the now known date of 1700, just by accumulating all this information and the incredible stories they use. If you have to convey this natural hazard in a way that people are going to remember it, you use stories of thunderbirds and whales battling that create shaking of the ground, that create waves and tsunamis. And I highly recommend this short paper if you haven't seen it, because it's really an amazing depiction of how information got passed down in the absence of the written record. Since that time, we've experienced an advance in our understanding of this landscape. My friend Jim O'Connor, who has probably been in your world a few times, is one of my favorite people to talk to, because he always has some tidbit that he's gleaned from the history of geology. And he put me on to James Dwight Dana, one of the godfathers of mineralogy and geology, and a Yale professor. And he was a scientist on the Wilkes expedition that was touring around post-discovery era, they weren't looking for new worlds, they were basically looking at what was in these worlds all over the Pacific. And looking for resources, looking for trade routes, and there was an armada of ships that is depicted here. And if you look at the path, the trajectory of the Wilkes expedition, they started in the Atlantic and made their way to the Pacific. Notice how much time they spent in Hawaii. They knew something good when they found it there, and there was lots of good reasons we have to keep going back to Hawaii to understand the landscape. I can imagine we all have similar feelings, but they made it as far as Antarctica. One of the things they were doing down there was basically confirming that it wasn't just a big block of ice. There was actually ground, there was land underneath it. And so confirming what actually was down there was a pretty big mystery for quite a while, time in New Zealand and so forth. The big reason though I bring it up is because here, they ended up and they concluded close to the end of the expedition, they ended up crashing one of their ships off the coast here in Portland on the bar where the Columbia feeds out to the Astoria Fan. And that's depicted in this painting right here, the wreck of the Peacock. And that led Dana and his party to get off the boat and make their way down to San Francisco by the inland route. And they saw things like this, Saddle Mountain, things you might know about here just to the west of you. However, and I apologize, I'll read the words behind that. Dana was, like a lot of my colleagues at U of O, was unimpressed with these trees that were in the way of his rocks. And so he said, this whole region is broken with hills of little seeming interest, bristled with evergreens, presenting little in general that is striking an outline. So trees like this were a problem. You had to get down on your hands and knees if you wanted to be a geologist when you were in Western Oregon. And Dana was one of the first to talk about that and keep on moving. So to introduce you, and you know this, it's to your west, but if I drop you into Oregon to the wet side, notice we're dropping into the green half of the state. I'm going to show you exactly what Dana was talking about. The Coast Range looks like this. It is steep, it's highly dissected, it's shaped by landslides and big trees and rivers, and it's remarkably consistent. I challenge you to figure out different locations based on the shape of the landscape because everything looks the same. It has been shaped by forces that have produced this incredibly characteristic, incredibly regular looking landscape over millions of years since it's been uplifted out of the Pacific. And that is what, to a geomorphologist's eye, is remarkable, not because of iconic, charismatic landforms, but just how systematically the landscape is responding to this uplift in climate and generating such a remarkably uniform landscape. So what is behind all those trees, might you ask? And so what's hidden by that green veneer, we now have the ability to better understand and characterize and quantify. And this is this new tool called Lidar. So this is not a photo, but an image of Lidar data whereby every single pixel that was detected from this airplane is colored according to whether it's a tree or the ground. And we see this nice meandering, quite pleasant looking river in the foreground and a gentle looking hill slope. But if you strip the trees away, Scott Burns' world is there. Giant landslides impinging down on this meandering river that have characteristic flow features, have gullies, even have a nice sag pond up here so we could understand the history of this thing. And so you just wouldn't know that that's there without the ability to see through the trees. So this transformation of being able to understand the landscape in this glorious detail has happened in my lifetime. And Scott and I were talking about this very thing. So when I was a geology student as an undergraduate at Stanford in the early 90s, we were given a map that looked like this one with contour lines. And that's one of the things we still teach our students. Don't think we don't, require them not to understand these maps. That's still really important to us. But we were given these maps and told to fill it in with lines, try to understand what's out there. And we spent a lot of our time trying to figure out where the heck we were on these maps. And any geology student that's done this knows exactly what I'm talking about. You have your compass, you have your bearings, and you need to triangulate where you are compared to prominent landforms and other features. And it was great, but it was a lot of time. Contrast that with what we now know. So that's that same area depicted with airborne LiDAR. And I would hazard to say that this massive revolution in our ability to resolve topography has completely turned the tables. Because when I was looking at these types of maps, I was trying to figure out where I was on the map in order to put our observations down there. And I've been in many situations in my career using LiDAR data in the field. So we have these data on our computers, on our phones, we're walking through it. And I've come up and realized there's a landslide in front of me because the LiDAR shows it, but I can't see it because it's behind some trees or bushes right around the corner. So it's completely shifted how we do field work and what we can do by allowing us to be more precise, more efficient, more targeted in where we go and gather observations. So here's a little zoom out of the kind of things that Scott and I get excited about. Beautiful landslide pushing this creek around and some bank erosion over here. And so all kinds of great stuff you can do. We do this technology, and you've heard about it before, but it's something that's really defined my career because I became a PhD student right when this technology was coming into the fore. It's generated by aircraft, either from space or mostly airplanes. And these airplanes have the ability to shoot hundreds of thousands of laser pulses every second. And they're peppering the landscape with these pulses, and they come back whether they hit trees or the ground or a cow. I've been working in South Africa on areas, and we have laser pulses showing us the whole body of a giraffe or elephants, and whatever is there, it's going to tell you in glorious detail. So we spend time depicting and analyzing what's tree, what's ground in order to do our work. Google Earth is great, imagery is great, and here's a nice example of a river valley not far from Prineville on the right, but there's so much information in topography. And not just the river, but the previous locations of the river, the history of braiding, meandering, migration, avulsion, so much information that's important for restoration, ecology, for hazards, for resources of very many kinds. And I think we all have realized how much this is useful, and it's become a utility. I really think it's sort of in that same category as power and internet and other things that we depend on for modern society. And that's, I think, the case that's really been made quite well. So not only in Oregon do we have this LiDAR-enabled depiction of the surface of the land, really high resolution almost all over the state, we also have everything else, including forestry, trees, and so forth. So it's a resource for all of these fields. This is an animation of one of our field areas in Northern California, right on the Pacific coast. It's right near Cape Mendocino and the Triple Junction. And so as we rotate in here, we're gonna basically digitally separate, digitally deforest, if you will, the trees and show you, again, more glorious landslides and giant gully complexes. This was an area that was vastly overgrazed and has experienced a lot of erosion, but it's also tectonically going up very quickly. And then more recently, it's been home to a lot of marijuana plantations. So when I was doing our field work with my students here about 20 years ago, we had lots of interactions that were not the most comfortable ones because of areas that we'd run into that we were not welcome at. So it was helpful to know where those areas were in advance because of the LiDAR data, so we could adjust our sampling schemes as a result. So it's good for all kinds of things, as I'm showing you here. So what I'm going to do for the rest of the time is just give you some highlights, the greatest hits of some of the things I've been working on and been aware of in terms of how this technology has informed our understanding of volcanoes, tsunamis, and earthquakes more specifically, as well as landslides. So we have it all here in the Northwest. Teaching geology here is like shooting fish in a barrel to get people excited when you can go out to a landscape and really demonstrate all these things that are happening. So if you drive straight east from Eugene and do a cross section through the Oregon Cascades, you come across the high Cascades, and that's this magical transition where you go up the Mackenzie Highway and the landscape goes from the steep and dissected form to this broad lunar-like high Cascade landscape. We all know why. It's covered by recent volcanoes, both broad shield Hawaiian type volcanoes to the big high stratovolcanoes that we like to ski on and adventure on. And the contrast right here by the big fault in this big graben area is a really interesting area where Gordon Grant and others that you've heard from have done work. And the reason I want to highlight this one is because this is the source of Eugene's drinking water. If you spent time in Eugene, go drink some tap water, and I challenge you to find better tap water in the world. I'm not sure about Portland and Bull Run, but I would put Eugene up there as some of the best stuff you can find. My kids were raised in Eugene, and whenever we travel, they're water snobs because they will not drink the water anywhere because of this. So Clear Lake is fed by springs. Snow that melts in those big, broad volcanic fields comes out as springs into Clear Lake and a few other locations along this area. And then it is brought down to Eugene through some hydro work. So why is Clear Lake here? Well, if we take away the trees, the answer is because of all these lava flows. So these flow-like features here, that for you Zoom people is down here at the southern end of Clear Lake, have been progressively battling the river. So the Mackenzie has been coming down this edge of the high Cascades and it's been trying to flow along that margin. And the Sandhill volcanic area has been progressively sending flows down the flanks of that mountain, damming that river against that flank. And eventually the lava flows won. And so Clear Lake is there. It's been there for some amount of time. And if you were wanting to experience what that was like back a few thousand years ago, when those lava flows were really active, go to Hawaii. And just a couple of years ago with the Kilauea Rift activity and all the overrun villages in the last couple of years, that was very much what it would have looked like. This is the PhD work of Natalia DeLine, who worked with one of my colleagues, Kathy Catchman. I am not a volcanologist, but for me, this stuff is just spectacular to look at. So based on the LIDAR data, based on a lot of field work, Natalia dissected all those different lava flows to figure out their source areas, their timing, their mechanisms. She also used bathymetry to map Clear Lake. If you've ever been there, go out to the dock and you can see the the drowned trees. So trees that were growing in the valley floor are still standing upright on the base of that lake, and they are dated at about 3,000 years old. Natalia and Kathy got some scuba divers to go down and take chunks out of these trees and carbon dated them. So we've got this spectacular water resource in Eugene. It's only a few thousand years old because of this great little reservoir created all natural by these volcanic fields. So spectacular illustration of how nicely the LIDAR allows us to really pull apart the volcanic history that's underneath all those trees. So let's move north. So we were just down here along the Cascade Crest in Oregon. I'm going to take you up to Seattle just for a little foray across the border. And one of the great things that separates Seattle from this part of the world is the glacial history. Check out the fact that the landscape has these north-south striations because of the ice sheet that's careened across the Puget Lowland before retreating. So it has this nice marker that it completely beveled. It's like sandpaper going across the landscape in the last glacial maximum, and it gives you a great temporal marker. And one of the things that LIDAR did in one of its greatest hits up in the Seattle area is revealing previously unknown faults. So these are giant breaks, giant scarps cut through that volcanic landscape that were previously unknown. These are people's backyards. This is a highly developed, highly occupied area. And these things that had been used for landscaping locally were actually identified as being tectonic features. So these are crustal faults. These are not necessarily related to the big subduction zone, but smaller, shallow faults that Ashley Strag, a professor here at Portland State, works on. And the reason why these are interesting is because they're pretty active. They've had at least 4 earthquakes in the last couple thousand years. And one of them even caused a local tsunami in some of the Puget Lowland areas that are nearby here. So pretty important to realize that all these areas that we've been comfortably living on have a lot of interesting things happening around them. As you also can see in this picture, just to the left of those faults are back to more landslides. So here's some big collapse features, some rotational slumps along the flanks of the Puget Lowland as well. That brings me to Oso. This was a defining event for people that work on landslides, for residents of the Pacific Northwest. This event of 7 years ago took the lives of 43 people. And the challenge I always put forth to people is when you see this, it looks, and it is, a dramatic feature. It's huge. It happened in a couple of phases. This downdrop block came across here and it sent a wave of material across the valley floor at great velocity. And it was literally impossible to escape or to outrun this. Created a dam upstream that was subsequently cut with some help from some excavation that allowed it to not breach and create another catastrophe in the wake of that. The challenge, though, is this a singular event? Is this something that was anomalous or uncommon in this area? And as you look at all this forested landscape, these hill slopes around, you would think, is there much history of that? And this is where the LiDAR really demonstrated its utility. So this whole valley has been falling apart by the same process ever since the glaciers retreated and opened up this, this valley. The glaciers were downstream off the screen, but this valley was cut almost entirely since the glacial times. And we see giant landslide after giant landslide after giant landslide after giant landslide. And so the OSO slide that's depicted here in red in the middle of the screen is just the most recent of a progressive series of massive landslides collapsing across this Stillaguamish River Valley. This highlights the work of Adam Booth that I'll show you in just a minute. But what's been done with these slides is a very recent one that's not that old, 500 plus years ago, all the way to older ones that are 6,000 years ago and everything in between. And so those dates are generated by carbon dating. And I want to call out my former student, Adam, who did an amazing piece of work with colleagues at University of Washington, using the shape of the landscape to figure out how old these slides were. When a slide happens and it's very young, it's very sharp, it's got edges, it's got blocks of rock that are all jumbled up and still have all those fracture zones and so forth from when they came out of the hills. And after time goes, weathering processes, soil creep, other things smooth out all those jagged edges over time, and it generates a smooth feature like this. So by using those carbon dates and independent measurements of how old these landslides are with the LiDAR data, Adam and his colleagues were able to apply dates to dozens and hundreds of landslides purely based on their form. And it works remarkably well. So this is the type of maps that Adam and his group generated. And this was on the front page of the Seattle paper when they were able to do this work. So the most recent ones, young ones in red, few hundred years, all the way to older ones greater than 5,000 years in blue and so forth. So another incredible example of awareness of the landscape, awareness of the rates at which this process happens would be incredibly useful for monitoring. If we knew this information, we would have a very different approach to putting sensors out to try to understand the dynamics of these and be able to use some of the modern tools we have to try to make these areas much less dangerous. So that type of awareness is exactly where I think geology needs to go. We need to use this type of information to help inform communities. Now, here's your next quiz. Where are we in the world? There's a clue in the lower half. This is a LiDAR image somewhere in the Willamette Valley. I'll give you a hint there. What does that thing look like? Does everyone see this little?
It's like a cinder cone.
It looks like a what?
It looks like a cinder cone.
It does, but it's a little bit perfectly shaped. It looks like an O.
Could we have iceberg
Is that
from the Missoula flood?
Eugene?
That's Eugene. That's Autzen Stadium. There you go. Yeah, Stadium. Right. So there we go. Even our football stadium looks like a giant O. We've got it sorted out. So Skinner Butte right here, Autzen. This is
Skinner Butte. Yeah, I know Skinner.
Skinner Butte. And you got I-5 going right there. The Coburg Hills right there. You got it. And so if you're in Zoom world, we're looking at I-5 right up north-south here. Yep.
Spores Bridge.
You got it. One of my favorite areas to stand up paddle down the McKenzie right there. So what I want to show you is probably something you haven't seen before. And that's this red box area. And I just showed you OSO.
Oh, wow.
That feature is 3 times as big as OSO. Coming out of the Coburg Hills, it just missed hitting I-5. I'm just kidding, it's a lot older. But we don't know how old it is. We haven't used the roughness techniques that Adam developed to date it yet. but we're at some point going to go out and also find some other ways to date it. But this type of feature is not uncommon in our state. And thankfully, Scott students, people like Bill Burns and others, have been systematically helping us understand our surroundings for the last couple decades. And they recently finished compiling all this landslide mapping in the Eugene area and developed maps like these that show us where these big features are, as well as small ones that help us understand the landscape around us. So all that is available to you, as you know, through the Dogami site and Slido. So the natural thing you might wonder is when you see a giant feature like that coming down next to a city like Eugene and on top of the subduction zone, the question people always want to know about is, are these things associated with big earthquakes? It must be the case that these giant landslides have to do with shaking. And this is something that people have surmised for quite a long time. This is a map of predicted peak ground acceleration on the left. These colors show models of subduction zone earthquakes on the Cascadia subduction zone and how the peak acceleration would be highest at the coast and decay as you go inland. But the reality is we have very few, if any, terrestrial records of these big earthquakes. I can't take you somewhere and say this landslide, this liquefaction feature, this fallen chunk of mountain is associated with the last big subduction zone earthquake in 1700. We just don't have that knowledge yet. We still have a big question mark when it comes to these terrestrial areas. So people have done models, created things like this. Mike Olson and others in the engineering group at Oregon State have done some beautiful work modeling it, but we still lack geologic constraints. So LIDAR to the rescue. In other parts of the world, when big earthquakes like this happen, this is a scarp created by an earthquake of 7.8 magnitude on the South Island of New Zealand near Kaikoura, where you can do some spectacular whale watching. Not only did it create a scarp like that, it triggered 25,000 landslides. Many of these took out the coastal highway for months, and many of them created giant landslide dams. Here's a big one right here on the right picture in the lake shown just upstream of that. And many of those are still there today. So is there an analog in Oregon that we can use to try to understand whether we have the record of giant earthquakes lingering out there somewhere in that broad green area I just showed you called the Coast Range? That's the work of my recent PhD student named Will Struble. The maps that we are going to show you are done in conjunction with Bill Burns and Nancy Calhoun at Dogami. Every little red dot on this map of Western Oregon is an ancient landslide that impounded a lake. So 15,000, sorry, I'm revealing the news before I get there. Sorry. So there's at least 15,000 old ancient landslides in Western Oregon. Several hundred of them have impounded channels, not unlike that New Zealand example I just showed you. So this red feature came down, dammed a river, created a lake. Same thing here on Yellow Lake, same here on Burchard Lake. There is a spectacular constellation of these that are out there in the trees waiting to be studied by geologists. So that's what we did. We went out because none of these have yet been linked to a magnitude 9 earthquake. We don't know if these things are associated with that last 1700 event, which happened on January 26th at about 9 p.m. based on the tsunami that eventually made its way to Japan. So these 200 or so red dots impound small streams, and the key is they have a chronometer in them. They have a tool that's preserved in that lake that we can use to figure out when these landslides happened. And that tool is Dendrochronology. So here's how we've gone about this. This is our first site that we did this technique at, and we've done it on 24 of these lakes since. This is hard work. We have help with field work and through the analysis that I'll tell you about in a second. So this is LIDAR data of the trees of this little fishing lake. If you're a fisher person, you might know about Watson Lake. It's a beautiful little slice of heaven in the middle of the Coast Range. It's really hard to get to. That lake exists because of a landslide dam, just like the ones I've been talking about. And it is preserving some drowned trees. This is what we call a ghost forest. So these are trees that were drowned by the flooding of that upstream valley and preserve the timing of that. This is what it looks like to go there. It is spectacular. It's very serene. It's very quiet. So there's this whole forest out there. And if you can get to the wood that's below water level, it has been relatively well preserved. The stuff above water decays, turns to this after a couple hundred years. But if you get down to some of the wood below the water level, it preserves the tree ring record in glorious fashion. So this was our resource. This was our data set. And so getting out there at the right time to get chainsaws, to get little slivers of these trees took a lot of work. Here's Will and I. And what you're not seeing in this upper right picture is there was ice on Klickitat Lake when we were there on that day. He still talks about that day in the field. Yellow Lake here is in the lower right. So these really amazing little slivers. And here's the technique. The key is you need live trees that are still going, that preserve the tree ring record, the barcode, as far back in time as we can. So these trees right here I'm showing you are from the study of Brian Black. He's our Dendrochronology colleague. He's now at the University of Oregon, and he's got trees from around Mary's Peak. He's got trees just south of there and a few other of these oddball spots where we still have trees that were alive in the year 1600 and even before that. So there are some old growth trees out there, and Brian is very keen at getting tree ring records using techniques like this with the tree core or increment borer and producing records like this. So this is the tree ring with record over trees that are over 400 years old. And so the key thing is you take out the growth patterns and you look at all these anomalies. So trees grow rapidly early, and then they grow at a much more typical pace since then. All the ups and downs around that record dry years, wet years, and so forth. So this is your barcode right there. That's the stuff that's left over from that general trend of how trees grow. So what we would do is we would take,
Don't you need some bark on the dead trees in the water to give you your date of death?
For those of you who couldn't hear, Carol says, don't you need bark on the trees from our drowned forest to do that? And we did. So that's why sampling them below that water level, we were always only using trees that had bark available. So we knew we had a complete record. Absolutely. That's an excellent point. So this is the barcode I just showed you of these living trees from Mary's Peak. Here's the little chunk of barcode from that chunk of wood from Klickitat Lake. And this is not how we do it, but this is visually hopefully appealing. And you can see, you can match it up in a way that statistically is by far the only explanation for the age of this tree. And this particular one happened in 1751. I thought for sure this was going to be the one that was 1700, but it was about 51 years too late. So it didn't match up with this last subduction earthquake. And so we've gone out and we've dated 20 of these dams. And this, I really want to emphasize our colleagues, Will Struble and one of his field assistants, Logan Wetherell. It is really hard getting chainsaws underwater and getting out to remote locations to get these types of records. After going out and doing that for 20 of these landslide dams, none of them have thus far coincided with the last subduction zone earthquake. Instead, what they have clustered in time is during big atmospheric river floods. So there are some historic floods in the 1880s, and we saw a cluster of landslide dams near the Umpqua River that happened in 1880 because of this big historic storm, and a few others that cluster appear because of atmospheric conditions. Some of these landslides actually happened even before 1700 as well. So whether we're looking for a needle in the haystack or we just haven't gotten lucky yet, we're not sure. But there's some amount of these still out there that we are still going to be looking at progressively. So the signature of these big earthquakes is perhaps still eludes us, but there are a lot of other things we've learned about these landslide dams as a result. So the last thing I want to tell you about in terms of this tool is something that's more recently come into the awareness of anyone living in the Pacific Northwest, and that's fire. So in September of 2020, if you are in this part of the world, you cannot forget what happened when that east wind came and blew down power lines and other sources of ignition across Western Oregon and created this massive conflagration series of events across our state. I will never forget it. The concern that came after this was whether subsequent rainfall events would cause destabilization of these burned areas and do things to Oregon that we've seen happen in California and other parts of the world in terms of mud flows and hazards. This is what it looks like in Southern California. This is a view of hill slopes above the town of Montecito, right outside of Santa Barbara. And when you burn the chaparral, like what happened in December of 2017, the Thomas fire burned these slopes. And about a month later, a very, very strong rainstorm happened. This is what happened. So that rain was unable to infiltrate into the ground. Instead, it ran across the surface, cut all these rills, entrained all this material, and coalesced and collected in these channels and sent debris flows through houses, through the communities, and killed 23 people. So there was dozens of these events, 3 or 4 really big ones that caused most of the damage. And these are the kind of things that Oregonians were thinking about because they were just happening at the same time down in California. The event that really got us thinking about this even before that was the Eagle Creek fire that happened in 2017. And so what I want to first point out before I go there is that thus far, we have not seen that Southern California style. We haven't seen this process play out in these fires thus far. So far, they have not produced these types of events for reasons that we're working on. And there's a whole nother talk I could give you talking about to walk through why that might be the case. However, we're learning a lot from this fire that happened 5 years ago, which was the Eagle Creek fire just up the road from you. Another defining moment for Portlanders, I can imagine, looking across to your east. So this is what that area now looks like, or did look like that following summer, where you can see little patches of green interrupted by broadly burned areas in the gorge on the Oregon side of the gorge. And what I want to do is show you the things that you might not have noticed about the landscape that are revealed by Lidar. So that's the footprint of the Eagle Creek fire. We're going to do a little virtual helicopter ride or parachute trip, if you will. We're going to fly in and rotate. So we're now looking south, looking up Eagle Creek right there down the middle. We're going to migrate over here towards the town of Dodson, and Multnomah Falls is just off to the right. And one of the things that you might not have noticed when you're driving up the gorge is this. So as you look at this area around Dodson, and Scott and I were just talking about this over dinner, you have these big features that we call fans. So these are giant piles of sediment that have been accumulating off the flanks of the Columbia River Gorge ever since the Missoula floods. I think Scott and I would probably agree on. And so that is an incredible amount of erosion. That's an incredible amount of sediment transport, but it all happens through landslides. So the mechanism by which these hills turn into this material is through debris flows and landslides primarily. And the question is, to what extent has this been facilitated by fire is the big risk. And that's what I want to show you some recent highlights of. So this happened almost 3.5 years after this big fire. So these debris flows started as very small landslides in that very area I was just showing you. So this is a small landslide scar that is about the size of my stage right here. And it proceeded, I should say, to mobilize, turn into a debris flow, go down valley, and there's another one up here, and some others that coalesced and did the same thing. And the reason these things became problematic is they initiate up high on these slopes, and as they flow downstream, they collect all the water, sediment, and material in the Channel Valley. They're incredibly effective at bulldozing and training all that material that's been collecting in these valleys. And as a result, they can be 50 to 100 times bigger than they started by the time they get out to these lowland areas. This particular event was fatal and took the life of a motorist just on the off-ramp right here. So this is that same feature, sourced way up here, coming across those big fans out here right onto I-84, which was closed for some amount of time as well. So we are very interested in how these things get started. And what I would tell you is that our best explanation currently is that trees are a big part of this. So back to that central theme where I started. The trees are also primal components of how this landscape, or primary components of how this landscape works. They provide nature's rebar for holding all this soil together. And just like if you cut trees down, they have a root network that can become susceptible and weak after clear cutting. Fire does the same thing. And so this is exactly the amount of time after which those root networks are much less able to hold on to that material and become problematic for shallow landslide initiation. So 3 years and about 4 months after the Eagle Creek fires when this happened. And we have done studies from my former master's students that's used historic fires to document that time scale of root decay and loss of strength. So we think the Columbia River Gorge is in this period of vulnerability because of this declining root strength. And it's something that we should be very aware of in terms of rainstorms that might be triggering these events. And sure enough, 2022, I should say, this few months ago, several dozen more of these landslides have come down through the gorge. So this is an area that's very active now because of the fire and probably will continue to be. So LIDAR to the rescue. It's a great tool for documenting what it looked like before, for trying to predict where these are likely to happen and where they're likely to go. These are two of my PhD students. That's Will Struble and Brooke Hunter looking at our visualization lab in U of O with LIDAR data in glorious 3D. And here's Brooke out in the field in some of these post-fire areas. These are nice before and after maps of a similar debris flow after a fire in Southern Oregon, which is very similar to these ones in the gorge. So I'm going to close by saying that LIDAR is part and parcel of how we do geology now. It's unimaginable to go out and do work without having this depiction of the landscape. It's also a bipartisan issue. LIDAR is big part of the National Landslide Preparedness Act, which was signed into law on January 5th, 2021. And it had Republican, Democrat senators all throwing their support behind this, and is now allowing the USGS, U.S. Geological Survey, to expand their work in our part of the world and elsewhere to better understand and characterize our hazards. The 3D program on the right is generating LIDAR all over the US and in a manner that we have been experiencing and enjoying in Oregon for a while. So Oregon has been at the forefront of collecting LIDAR data and using it to understand our landscape. And we have been so appreciative of Dogami and their work in doing this over the years. So Ian Maiden, Bill Burns, and others have been generating the Oregon LIDAR Consortium, which has all this great coverage for students, for contractors, for anybody that wants it in the general public. Was that a question, Carol?
Well, I was just going to ask about the financial mechanisms by which this is being done. Ian's told us more than once that he has had to get data wherever he possibly could from commercial sources and things. So is that Bill that you were telling us about financing some of this? How is this being done?
Right, so there's now going to be more federal money thrown at this. In theory, they would fly every state, every 6 years or so. And so not only do we have a single snapshot, but we have this regular acquisition schedule. Now, the money, the appropriations are obviously a question mark. And just because we have the act and they have the plan doesn't mean the funds have happened. So far, so good because of pandemic investments in infrastructure and things like that. But keeping the momentum up is great. What Ian did in the meantime is truly remarkable by building a consortium of local, state, federal agencies to build this Oregon LIDAR Consortium. We have a small geomorphology conference called the Brett's Club, and one year we honored Ian and all had t-shirts about LIDAR and Ian, and his picture was on our t-shirts. So he holds a special place in our heart because of what he's provided with our state. But I think it'll continue to become more of a utility and part of our investment in places. So if you haven't seen this is something non-geologic, but it also can be used in all these other fields. This is in Guatemala. There's other examples in Central America and elsewhere where anthropologists had been working on these Mayan civilizations and had calculated how many people lived there, what it looked like, and then they mapped it with LIDAR. And they realized they were mapping Portland, and in reality it was Houston. And they realized that there was hundreds of thousands of more people in some of these ancient Mayan civilizations. My favorite quote ever about LIDAR is you just have to sort of bow before the LIDAR and accept that it's better than you are. And that is something I have come to accept, and anyone else does as well. So the key thing here, as my final slide, is that it doesn't supplant field work. We still have to go out and generate samples to analyze them, to understand the timing, the context. A lot of things still require us to go out in the field. So this is not a replacement for that, but it allows us to do our fieldwork better. Allows us to be more informed and more effective geologists, be safer, and so forth. It's incredible tool for basic applied work, and there's all kinds of things we probably don't even know yet. For me, the aesthetic value of LiDAR is just as important as the scientific one. This is a map inspired by Daniel Coe, who's one of the geniuses of LiDAR visualization and cartography. And I made a map in his mode of looking at the relative elevation of the Willamette River, meandering somewhere near Salem. And you color the LiDAR data based on elevation. So light areas are really low. That's where the river is now. Dark areas are high. Those are floodplains. But it just, you can see any number of different things here. Everywhere from, I see like a jellyfish to, you know.
That's a Sandy Arm River, I think, coming in from the west, from the east.
Over here.
Yeah.
This looks like lightning to me. Yeah, and so you've got the little Sandy Am and these other tributaries coming in. So we can and we do make posters of this kind of stuff, because not only does it help you understand the landscape, but it's just really nice to look at. So a lot of people contribute to this. Again, Ian is at the top of that list. His colleague Bill, Ian's recently retired, still keeping busy as far as I can tell. Bill, Burns, Nancy, my students, a bunch of students, and Jim O'Connor and others. And so I'm really just telling you a lot of things that I've learned from them as well. So thank you for your time, and happy to answer some more questions. Yeah.
I'm a geological novice, not a professional a little bit. About 15 years ago, I started discovering these LiDAR images of Oregon. And then I started trying to find LiDAR images of Washington. They're much harder to find. And it made me think, well, what's driving the LiDAR research and implementation? Is it like the state universities? Is it the geological departments of each state? It seems to me like it should have been a national federal thing, but it doesn't seem to be like that.
So
and I presume that Washington
Repeat the question, Mike, and then we'll take a
was
question.
much easier
got it.
to view Oregon back 15 years ago than it was.
Yeah. That's a great question. The question was, why does Oregon have such a good LiDAR history, and where does it come from? Who's paying for it? How does this come about? Is it systematic, state, federal? What's the story? I'll give you a little bit of a personal history, and then a little bit of what I know, and Scott, please chime in as well. I was a PhD student in the mid to early 90s, and I just happened to be lucky enough to be working in Bill Dietrich's lab in Berkeley when he got turned on to LiDAR. And one of the very first LiDAR data sets was in Coos Bay area here in Western Oregon. And we used it to do geomorphology. And it was a little postage stamp of about 5 kilometers by 2 kilometers. And at the time, we thought we were the richest people in the world to have this data set. We figured out a lot about how the landscape was working and applied it towards all that green, steep topography at the time. At the time, we assumed that it would become a federal asset, become a federal service. However, at the time, a lobbying group that represented all these LiDAR vendors prevented that from happening. So the USGS had a plan to basically tool up, buy their own LiDAR equipment, but some well-placed lobbyists representing all these private vendors prevented that from happening because they were making lots of money getting hired by utilities, by communities to map everything from power lines to developments to you name it. So there was a really strong market force early on and political influence that prevented that from happening. So it's only been till decades later that we've seen the federal government really say, no, we got to get serious about this. And that's this 3-depth program that I just mentioned, where they're going to start more systematically mapping across the various states. Now, Oregon was at the forefront because of Ian, because of Dogami. So your state geology agency is a leader, is a pioneer in realizing the value of this technology and utility, building local collaborations and pooling funds to get, once you get an airplane up in the air, it's a lot cheaper to keep it flying than to get it to that area. And so they knew by making areas bigger and bigger and bigger, the cost, the incremental cost was decreasing rapidly. So it's really about mobilization costs and not about less about hours in the air. And so they were just amazingly effective at building different groups and funding from all these different levels to basically piece together that whole map of Western Oregon. At that very time, there was no equivalent in California, nothing. There's no, you couldn't go to any website and had any publicly available LiDAR for the whole state of California. Remarkable. Same thing was true in Washington, as you experienced. Now, since that time, Washington has learned from their neighbors to the south, and they are actually doing the same thing. There was a Puget Sound LiDAR consortium run by a guy named Ralph Hagerud at the US Geological Survey at the time, but it wasn't sort of the scope and the amazing expanse that the Oregon one was. So Washington is embarking on the same thing, and they are going big and broad and statewide, probably faster than Oregon because they have more money to throw around at the state level. But it's really because of our lead and Ian's leader vision that that's happened. So yeah, Scott, what would you add?
Every state's different. I still remember 23 years ago, state of Pennsylvania flew the whole state. And all of that LiDAR was available to everybody.
Yeah.
And so they made that decision.
Yeah. And I will say that the quality of the LiDAR is variable. So Pennsylvania was one of the states that decided to fly everything, but they didn't do it as quite as high resolution as we would want it out here to get through all these trees and so forth. So there was ways to sort of, do it in more cost-effective ways. But it was a state-by-state, absolutely thing.
Let's take a question from the chat.
Okay.
Are there other examples of where Native American historical records provide geologic insights? Do Pacific Northwest Indigenous people have calendars that can be correlated with Western cultural calendars? And that's from our friend Gary Joplin.
Jerry, that's a great question. I wish I had more to tell you. I think it's an area of opportunity. I have a project in Sitka, Alaska, working on landslide hazards, and it's with a group of risk managers, social scientists, anthropologists, and we've developed a landslide warning system for that community of Alaska, and it has involved the Sitka tribe, as well as the city of Sitka and other agencies along the way. And part of our work involves interviews with elders to understand how they talked about how they process landslides from their ancestors in the oral history. And so they're still in the process of acquiring and gathering that information. But if you're in Southeast Alaska, there's big, tall mountains that are really steep, and then there's the ocean, and there's a very thin strip of land that you can live on a lot of these islands. And so you either have ocean forces, including tsunamis, or landslide forces, and there's not a whole lot of wiggle room between them. So those indigenous peoples that lived there for thousands of years were absolutely aware, and they knew where to migrate to in different seasons. But we're still gathering that information. Some of those records that I mentioned in that paper about the Cascadia subduction zone earthquake do talk about some landslide events, and there is some discussion of those along the coastal areas, but not in the inland areas that I'm aware of. So I think it's a neat opportunity, but I can't put my finger on other shining examples like that one I told you about earlier. Yeah. Is there another hand? Yeah.
Can these flights take place any day of the year? They need certain seasons or good weather?
Yeah, they do like to fly in good weather. So shooting lasers through rain and things like that is really problematic, and also just because of the stability of the aircraft. In this part of the world, we try to fly in leaf off conditions. So either before the spring foliage comes out, or right when the fall happens. And also you have to contend with snowpack in the winter as well. So there's all kinds of forces, and depending on the area you're flying. So yeah, time of acquisition is definitely something we have to think about when we're making these flights. I will say that I was just on a Zoom meeting this past week with a company based here in Portland, and this is becoming more common, but they're putting LiDAR on drones. And when we say drones, I don't mean the sort of things that teenagers get for our grade school kids for Christmas, but like big $100,000 drones that are able to go up to these really steep gorge areas and get data in some of those really remote, rugged settings. And so that gives us a little more flexibility to be under clouds and things like that. So it gives us a broader window within which to work. And so we're just about to start collecting that data in the gorge for those debris flows I was just showing you.
Okay, from the chat. Is anyone looking at debris flows or increased flash floods due to clear cutting? Is this just like a fire reducing root anchorage of soils? That's from Michael Nunzert.
Yeah, Michael, good question. So that is where we got started with this. And some of the work we did back in the 90s was after the 96 storms, when thousands of landslides were triggered across Western Oregon, including 2 fatal ones, one near Roseburg and one near Scottsburg along the Umpqua River. And so both of those were sourced in clear-cut areas. So far, our data says that if you kill a tree by cutting it or burning it, the decay of the root strength is about the same. So after 3 years, it has about 80 or 90% loss of its strength, only within 3 or 4 years. And that's why we think we're seeing all this activity in the gorge, is because it's after that 3 to 4 year time period. And we're basically waiting until the new trees come in and establish that network of roots to reinforce the soils again. So it's very similar story with burning or clear cutting in terms of that root reinforcement. The flash flood story I'm not as familiar with in terms of the hydrologic role, but there are some work, some studies out of Oregon State about clear cut effects on flood peaks and so forth. Yeah.
Has the Lidar actually, in practical terms, changed human endeavor as far as building or roads or at this point?
The question is whether Lidar has changed the human endeavor in terms of development, roads, infrastructure, how we encounter and do our thing on landscapes. It really depends. In some ways, yes, in terms of affecting where development happens and doesn't. Landslide areas all over the Portland Hills, as Scott can tell you much better than I can, are absolutely informed by this. So in some cases, it's been after things have started to move. And in other cases, it's when we're now able to anticipate that there's areas we probably shouldn't venture into. So landslides are one of probably the simplest. The Lidar is also redefining tsunami inundation zones. So all the coastal towns in the Oregon coast and elsewhere along the Pacific have been remapped for tsunamis based on Lidar. And the ability to map the inundation zone is greatly increased with this tool. So that's another one. Flood hazards, the FEMA 100-year flood zone had to be remapped with Lidar in a lot of these areas, just because small changes in elevation can have a huge impact on flood inundation. So you name it, whatever superficial geologic process is out there, Lidar makes us be able to characterize it much, much better. And so that's from a sort of hazard mitigation perspective, but for infrastructure too, there's the civil engineering world. They do this, they are in love with this technology just as much as we are. And in terms of scanning bridges, they use it to evaluate infrastructure as well. So it's truly useful. I mean, a lot of the early self-driving cars had Lidar on their roof, and they were constantly scanning around the car to figure out who else was nearby and how fast they were going, how big they were. Was it a person? Was it a car? And so Lidar versus cameras for self-driving cars was a long debate for a while, with Elon Musk coming in with cameras and imagery being the dominant way that Teslas do it now. But for a while, a lot of those early self-driving cars were informed by Lidar on the roof.
David Davis Van Atta asks, do we have reliable estimates of the strength of the 1700 earthquake as manifested in the coastal range region west of Eugene? He had the sense that there was a full rip along the length of the Cascadia fault. It was perhaps highly centered well north, perhaps peaking even north of Seattle. Perhaps the lack of a year 1700 landslide in Impounded Lake suggests richer strength less than estimated in far western central Oregon.
Yeah, that's a great question. David, was it? David, yeah. I would be really hesitant to say that our inability to find landslide dams is a good piece of evidence yet to, to dismiss or dispatch big earthquake shaking. So I'd be very cautious making that, but it is still curious that we are struggling to find the signature of these big events. There is still the predominant mindset view paradigm that the last 1700 event or that 1700 event was a full margin rupture. There are colleagues of mine that think that that's actually needs to be reevaluated based on the geologic evidence and modeling. So there are some recent efforts to revisit that assumption in a more detailed fashion. But the kind of work we're doing is helping to inform that in terms of where we don't see evidence of shaking. But it is really curious that we still really can't put our finger on any terrestrial record when the offshore record is just incredibly rich with turbidites and other features all along the seafloor that tell us about that last event. So good question, and I'll get back to you. I don't know how long it'll take.
Next question.
We got one in the front.
How valuable is LiDAR in urban areas like Portland?
Oh, great. It's good everywhere. Depends what you want to map. What's that?
What does it add? I mean, we're able to go all over the place on foot in Portland.
Sure.
What do we see with LiDAR that we can't see on the ground?
Well, I mean, certainly buildings and a lot of things that you might not know are out there. But like in Seattle, that example of a fault scarp going through a neighborhood is a great one. Not to say that we're going to see anything here in Portland underneath all the concrete and asphalt, but certainly for mapping the infrastructure, it's a tool that is constantly being used for that, by a variety of fields and disciplines. Yeah.
You said the data in California is a lot more scarce than in Oregon. I would think one place that they really have an interest in studying would be along the Hayward Fault.
Yeah.
The East Bay.
Yeah.
So there is an effort so the question is, what's up with California? Why the heck don't they have some LiDAR data? Because they've got faults, San Andreas, Hayward Fault. You're right. And so I want to be clear that they don't have a public facing database like we have. However, the National Science Foundation has funded extensive LiDAR acquisition in California for very specific reasons. And one of the things they did is they did a project called the B4, so a big B and the number 4. And that was basically flying LiDAR on every active fault with about a 2-mile wide radius to provide a baseline so that when earthquake events do happen, we know what it looked like before that earthquake. So the San Andreas, all the way the length of the whole fault, the Hayward Fault, Calaveras, you name it, Rogers Creek, all these faults that are active in California have been flown. And there is a widening footprint of publicly available, but it just isn't managed and accessed and are accessible in such a fashion that we have here in Oregon. So.
One more question from the chat from Carrie Gordon. Has anyone started looking at the landslides across the Ochiko Mountains and the rest of the Blues? I noticed the melted modified landslides form versus fresh in the rotational landslide.
What was the name?
Carrie Gordon?
Carrie Gordon, great question. You just gave me a good thesis idea for a student. Her question about the Ochikos in that area. There's all this melting oozy topography that's like, again, get me and Scott and our students really excited. I haven't seen anyone really start to study that or try to understand it, but it sounds like it's a low-hanging fruit that someone ought to pick up and take a look at in more detail and to see what's triggering and what mechanisms are at play there. Because I've seen some of those, but just never had the time to really dig in that much. So that's a nice area to work to.
So thank you for all the questions. Josh, absolutely wonderful talk. I mean, how about a round of applause?